Welcome to the deep dive. Our mission today, well, it's a pretty focused one. We're going to cut through some of the complexity in machine learning source material. Specifically, we want to zero in on one of its core pillars, supervised classification algorithms. You've provided us with a really comprehensive breakdown, a lot of material on how we teach computers to categorize things, to put labels on the world. Our goal here isn't just, listing methods. It's about synthesizing the different approaches, the trade-offs you inevitably face, and the features that really define success, understanding the ways engineers tackle this labeling problem.
That's right. And our starting point has to be supervised learning itself. It is one of the main types of ML after all. The core idea is quite straightforward. The algorithm builds its model from a training data set. And crucially, this data set includes both the inputs and the desired outputs, the answers basically. So it's learning with a guide, a teacher.
Learning from examples. Okay, and we need to make a key distinction right at the start, don't we? Classification versus regression.
Absolutely critical. It's the difference between asking what kind versus how much. Classification predicts the categorical outcome. Is this email spam or not spam? Or maybe, is this medical image showing something malignant or benign?
So distinct categories.
Exactly. That puts you squarely in classification. Regression, on the other hand, that's for predicting a number like the price of a house or maybe the temperature tomorrow, a continuous value.
Okay, so before we even dive into the specific algorithms, we need to know what good looks like. How do we actually grade a model's performance once we've built it?
Right. You need metrics. And the absolutely essential tool here is the confusion matrix, sometimes called an error matrix. It's like an X-ray into how the model is doing.
The ultimate diagnostic chart, I like to think of it.
It really is.
Yeah.
Imagine your model is sorting things into, let's say, 3 classes A, B, and C. The confusion matrix gives you this 3x3 grid. The rows show the actual class, and the columns show what the model predicted. And the interesting parts are off the diagonal, where the system gets, confused. Where it maybe labels an A as a B, that's where you need to focus.
And from that grid, we can pull out the specific types of errors, right? We know the successes, true positives, true negatives, but the errors tell the real story.
Exactly. 2 main types of errors to watch. First, the false positive or type 1 error. This is the model saying yes when the answer is actually no. Think of like a spam filter catching an important email. Annoying, usually.
Right, an error of commission. But the other one, the false negative, that often feels more serious. Type 2 error.
It often is, yeah, because that's an error of omission. Failing to flag something that was there, like in medicine, missing a disease diagnosis, that can be much, much costlier. Which is why we don't just stop at the matrix. We calculate scores like precision, sensitivity, also called recall specificity, and the F1 score. These all weigh the different kinds of successes and failures differently, depending on what kind of risk you can tolerate for that specific application.
That makes a lot of sense. So zooming out a bit, beyond these specific scores, what's the ideal checklist? What characteristics do engineers want in any good ML algorithm?
Well, number 1 is high accuracy, obviously. But this is where a really key concept comes in. The balance between bias and variance.
Ah, the classic trade-off, the Goldilocks problem. Can you break that down? What's the danger on each side?
Sure. High bias means your model's too simplistic. It hasn't really learned the underlying pattern in the data. We call that underfitting.
Like it didn't study hard enough.
Kind of, yeah. High variance is the opposite problem. The model is too complex. It's basically memorized the training data, including all the random noise. It overfits. This model aced the practice questions, but fails spectacularly on the real exam because the questions are slightly different. It can't generalize.
So you need that sweet spot, a model that generalizes to new, unseen data. Okay, what else is on this ideal checklist?
Speed is important, both how fast it trains and how fast it makes predictions. You generally want low sensitivity to outliers because real data is messy, right?
Always.
Limited use of memory is often a factor too. And something increasingly critical, especially in areas like finance or healthcare, simplicity and interpretability.
Yes.
You need to understand why the model makes the decisions it does. A black box can be hard to trust.
Okay, perfect. We know the ideal now.
Yeah.
Let's start looking at how some of the foundational classification models tried to achieve this, beginning with linear approaches.
First up, logistic regression. Now, the name is a bit confusing, but remember, it is a classification algorithm. It uses a logistic function, an S-shaped curve, to squash the output into a probability between 0 and 1, which then gets assigned to a category.
And the trade-offs. What do you need to watch out for?
Mostly practical things. Multicollinearity, where your input variables are highly correlated with each other that can cause problems. The model might struggle to converge to find a stable solution. Also, if you have more variables than observations, that can be an issue.
Got it. And then moving chronologically, we had a really foundational concept for neural networks, the perceptron.
Perceptron, yeah. Revolutionary for its time. It was the simplest supervised algorithm for binary classification, just 2 categories, a basic linear classifier.
But it had a massive limitation, right? The one that led to the so-called AI winter.
Exactly. Single-layer perceptrons could only learn patterns that were linearly separable. If you couldn't draw one single straight line to perfectly separate your yes examples from your no examples, the perceptron just couldn't solve it. And most real-world problems aren't that simple.
So if the simple perceptron hit a wall, how did engineers break through that linearity barrier? How did they start handling more complex real-world data?
Well, they evolved it into the single neuron with backpropagation. The big leap was moving beyond the perceptron's simple on-off step function activation. They introduced smoother, nonlinear activation functions and, crucially, used a gradient-based learning rule, the delta rule, leveraging the function's derivative to update the weights. This allowed the neuron model to learn nonlinear relationships. That shift from a hard step to a smooth curve really opened the floodgates for modern deep learning.
Fascinating how limitations drive innovation. Okay, let's switch gears completely now. Let's talk about an approach that doesn't really build a model in the traditional sense. K-nearest neighbor, or KNN.
KNN is, it's kind of the anti-model model. It's instance-based or memory-based. It doesn't learn a general formula during training. It just memorizes. It stores every single data point from the training set.
So it's like classifying based on who you hang out with. Social proximity.
That's a great analogy. When a new unseen data point comes along, KNN classifies it based on the most frequent class among its taller nearest neighbors in the stored data. Nearest is usually calculated using Euclidean distance, just the straight line distance.
What are the pros and cons there?
The big advantage is that training is basically instantaneous. You just store the data, and it's super easy to understand conceptually. The huge downside, though, is prediction time. If your data set is massive, finding the K nearest neighbors for a new point means calculating its distance to potentially millions of stored points. That can be incredibly slow.
Okay, speed is a factor. Let's move to another method known for its speed, but this one's probabilistic. Naive Bayes, NB.
Right, naive Bayes. It uses Bayes' theorem, a fundamental concept in probability, to calculate the probability of a data point belonging to each class. Its brilliance lies in its speed and simplicity. But the name naive gives away its big assumption, its potential flaw.
Which is?
It relies on a naive assumption of strong independence between features. It assumes that the presence or value of one feature tells you absolutely nothing about the presence or value of any other feature, given the class.
Wait, but that's often just not true in the real world, right? Like, knowing someone has a high income probably does change the probability they have expensive hobbies, for instance. So why use a model built on a premise we know is often flawed? Is the speed worth it?
It seems like a big compromise, I know, but it works surprisingly well in practice, especially with high-dimensional data like text documents. And the advantages are significant. It's very, very fast to train, doesn't need much memory, and the results are highly interpretable because you're dealing with probabilities. It often makes a great baseline model or a choice when you just need something quick and understandable.
And it's adaptable too, isn't it? There are different flavors of naive Bayes for different kinds of data.
Exactly. If your features are continuous and roughly follow a bell curve, you'd use Gaussian NB. For text classification, you often see multinomial NB, which works well with word counts, or Bernoulli NB, which just looks at whether a word is present or absent. It's a versatile family built on that core probabilistic idea.
Okay, so we've covered linear boundaries with logistic regression and perceptrons and proximity with KNN. Now let's look at methods that explicitly try to carve up the feature space into regions. Let's start with discriminant analysis, DA.
Yeah, DA's approach is quite geometric. The goal is to partition the entire data space into distinct regions, one for each class. Once you have these regions defined, classification is simple. You just see which region a new observation falls into.
And this leads us to linear discriminant analysis, LDA. Now, this one often gets mixed up with PCA, principal component analysis. How are they different?
That's a really important distinction to make. PCA is unsupervised. Its job is just to find the directions, the principal components that capture the most variance in the overall data set without caring about class labels at all.
It's just looking for the biggest spread.
Exactly.
Yeah.
LDA, on the other hand, is supervised. It knows the class labels, and its specific goal is to find the linear axes, the combinations of features that best maximize the separation between the different classes. Think of it like this. PCA might find the direction that shows the biggest difference in size among a mix of fruits. LDA tries to find the direction that best separates the apples from the oranges. It's optimizing for discrimination.
Okay, goal-oriented separation. But what if a straight line isn't the best way to separate the classes? What if the boundary is curved?
Then you might move to quadratic discriminant analysis, QDA. LDA makes a simplifying assumption that all classes share the same covariance structure. QDA relaxes that assumption. It allows each class to have its own covariance matrix. The practical result is that QDA can create curved decision boundaries, technically conic sections like ellipses or hyperbolas, instead of just straight lines or hyperplanes.
More flexibility sounds good. Is there a downside?
There is. Because it's more flexible and fits the data more closely, QDA is more prone to overfitting than LDA, especially if you don't have a lot of data points relative to the number of features.
Right, that bias variance trade-off again. Okay, moving from drawing boundaries to a more hierarchical approach. Classification and regression trees. CART. Decision trees.
Yes, cards.
Yep.
Decision trees build a classification model that looks like, well, a tree or a flowchart. It works top-down. At each node, or branching point, the algorithm asks a simple question about one of the input features, like, is feature X greater than value Y, to split the data.
And how does it pick the best question to ask at each split?
It uses metrics that aim to increase the purity of the resulting subsets. For classification trees, common metrics are the Gini index, or entropy, which is related to information gain. Basically, you want the split that results in groups that are as homogeneous as possible in terms of class labels. You're trying to isolate the classes.
Trees are incredibly popular, partly because they seem so intuitive, right? You can literally draw them out. What are the main pros and cons?
Pros. Definitely highly interpretable. You can follow the path down the tree to see exactly why a prediction was made. They're also relatively fast to build and can naturally model nonlinear relationships without needing data transformations. Cons. Their main weakness is instability. They have a strong tendency to overfit the training data, creating very complex trees that don't generalize well.
They memorize the training set too easily.
Exactly. And they're very sensitive to small changes in the data. A slight change in the input might result in a completely different tree structure, also sensitive to outliers.
Okay, that instability, that tendency to overfit, feels like a major problem, but it also sets us up nicely. If single trees are unstable, how did engineers tackle that?
Well, that leads us directly into some more advanced concepts. But before we get to combining models, let's briefly touch on support vector machines, SVMs. They found a different way to think about boundaries.
Okay, SVMs. What's the core idea there? What's the engineering insight?
SVMs, for binary classification, aren't just looking for any boundary that separates the classes. They look for the optimal boundary. Specifically, the hyperplane that has the maximum margin, the largest possible distance to the nearest data points of either class.
Ah, so it's maximizing the buffer zone.
Precisely. This makes the model very robust. The boundary is defined only by those closest points, which are called the support vectors.
But what if the data is messy? What if you just can't draw a straight line or plane to separate the classes, even with a maximum margin?
That's where the kernel trick comes in. SVMs can use a kernel of transformation, like the popular radial basis function, RBF kernel. If you can't separate the data with a line in, say, 2D, the kernel mathematically projects the data into a higher dimensional space, maybe 3D or even much higher. The magic is that in this higher dimension, the data often does become linearly separable by a hyperplane. It's a really clever way to handle nonlinearity using fundamentally linear methods.
Ingenious. Now, sticking with the theme of distance, you also mentioned metric learning, ML.
Right. Metric learning is often used in conjunction with KNN, since KNN's performance depends entirely on having a good distance measure. Metric learning algorithms aim to learn a distance function specifically tailored to the data, often based on the Mahler-Nobis distance, which accounts for correlations between features. The goal is to learn a metric that pulls similar items closer together and pushes dissimilar items further apart. An algorithm like LMNN, large margin nearest neighbors, actively tries to minimize imposters' points from different classes that are incorrectly close to each other.
Okay, interesting. So fine-tuning the very idea of distance. Now, back to those unstable trees. How do we harness their speed but fix their overfitting? Let's talk ensemble methods.
Ensembles. Yes, this is the wisdom of the crowd's approach. The core idea is, if one model might be flawed or unstable, Maybe combining the predictions of many models will give a better, more robust result.
And the classic ensemble method for trees is random forest, right?
Absolutely. Random Forest uses a technique called bagging, which stands for bootstrapped aggregation. You create many different decision trees. Each tree is trained on a slightly different random sample, a bootstrap sample of the original data, and often only considers a random subset of features at each split. Then, to classify a new point, you let all the trees vote, and the majority class wins. This averaging process dramatically reduces the high variance, the overfitting that plagues single decision trees.
So averaging out the errors makes sense. But there's another ensemble approach, one that seems even more clever because it learns from mistakes. AdaBoost, adaptive boosting.
AdaBoost is conceptually brilliant, yeah. It also combines multiple models, but typically very simple ones called weak learners. Often these are just decision stumps, single-level decision trees.
Just one split.
Just one split. But here's the adaptive part. AdaBoost builds the models sequentially. Each new weak learner is trained to pay more attention to the data points that the previous learners got wrong. It iteratively focuses on the hard-to-classify examples, assigning them higher weights. It's like a team where each new member focuses on fixing the mistakes the previous members made.
Wow, a self-correcting system. What's the outcome of that focused refinement?
You often get extremely high accuracy. AdaBoost models are very powerful predictors and tend to be quite robust, often less sensitive to outliers than some other methods. It really boosts the performance of those simple weak learners into a strong collective model.
Okay, that's impressive. Finally, we arrive at the current frontier, arguably, deep learning for classification.
Right, we're kind of coming full circle back to the neuron idea, but massively scaled up. The Multilayer Perceptron, MLP, is the archetypal deep learning model for classification. It's a neural network with an input layer, an output layer, and one or more hidden layers in between. These hidden layers allow the network to learn incredibly complex hierarchical features from the data. They use backpropagation, like the single neuron we discussed, but across many layers to adjust potentially millions of connection weights. They can model almost any complex nonlinear relationship.
But there's always a trade-off. What's the cost here?
The cost is data and computation. Deep learning models are data hungry. They typically need vast amounts of labeled training data to perform well, and training them takes significant computational power and time. Complexity goes way up.
And within deep learning, there are specialized architectures too, right? Particularly for things like images.
Definitely. Convolutional neural networks, CNNs, are a prime example. They are specifically designed for grid-like data, especially 2D images. Their architecture is inspired by the human visual cortex and uses a mathematical operation called convolution to efficiently detect spatial hierarchies of features, edges, corners, textures, objects. They dominate image recognition tasks.
Okay, wow. Let's try and synthesize this journey. We've gone from the absolute basics, defining supervised classification, the crucial role of the confusion matrix, through the early linear models like logistic regression and the limitations of the perceptron. Then we looked at instance-based learning with KNN, probabilistic methods like naive Bayes with its speed and, well, naive assumptions. We covered geometric approaches like LDA and QDA, the interpretability and instability of decision trees,
leading into the powerful solutions like SVMs finding that maximum margin, and then the ensemble methods, random forest, averaging out errors, AdaBoost learning from them, and finally, the immense power and complexity of deep learning with MLPs and CNNs.
It really highlights the sheer breadth of tools available, doesn't it? And the huge variation in what they offer.
Absolutely. You have algorithms optimized for speed and simplicity, like KNN or naive Bayes, which are great starting points or when interpretability is key. And then you have the heavy hitters, like AdaBoost or deep learning models, pushing the boundaries of accuracy, but demanding a lot more in terms of data, computation, and sometimes sacrificing easy interpretation.
So the core takeaway for you, the listener, seems to be that choosing a classification algorithm is never about finding the single best one. It's always about understanding the trade-offs. You have to constantly weigh what matters most for your specific problem. Is it raw predictive power? Is it speed? Is it how much data you have? Is it the need to explain the decision?
Which brings us to a final thought to leave you with. When you approach a new classification task, what's ultimately more valuable? Is it using an algorithm that offers high interpretability, like a simple decision tree, which can give you a clear why tracing the exact logic? Or is it better to go for maximum accuracy with something like AdaBoost or an MLP, even if it mainly just tells you the what, the final prediction, without an easy explanation? That choice really defines the nature and utility of your application.